Section 4.3, Properties of Logarithms. Let b, m, and n be positive reals with b not equal to 1. Then the logarithm of a product equals the sum of the logarithms. In this first example, we have the log base 6 of 7 times 11. So we can use the product rule to expand that to the log base 6 of 7 plus the log base 6 of 11. In example B, we have the log of 100x, so that equals the log of 100 plus the log of x. Notice that log is written without a base, so the base is 10. That means that the log of 100 can be simplified because it's the exponent we have to give 10 to get 100. Since that's 2, we end up with 2 plus the log of x. Now that one's simplified. You might wonder why part A can't be simplified because it just has constants. The reason is that 6 cannot be raised to a rational power to get 7, nor can 6 be raised to a nice power to get 11. So that one is as simplified as it can get. Now let's take a look at the quotient rule. It says that the log of a quotient is the difference of the logs. In this example, we have the log base 8 of 23 over x, so we get the log base 8 of 23 minus the log base 8 of x. There is not a rational power that we can raise 8 to get 23, so this one is simplified. In part B, we have the natural log of e to the 5th over 11. Notice that the ln tells us that the base is e. We can expand this by subtracting the logs, and then we notice that the natural log of e to the 5th can be reduced to 5. This is because we have our rules for natural logarithms, and one of them was the inverse property that says the natural log of e to a number equals that number. So this equals 5. The natural log of 11 cannot be simplified, so that's our final answer. The power rule tells us that the logarithm of a number with an exponent is the product of the exponent and the logarithm of that number. We often think of it as taking that exponent p and sliding it down in front. In example 3a, we can take that 9 and slide it down in front. In example b, we take the natural log of the cubed root of x and we first rewrite it as the natural log of x to the 1/3 power, and then the 1/3 can be slid down in front. And finally, we have the log of x plus 4 quantity squared, so the 2 can be slid down in front. Here's a summary of our 3 properties for expanding logarithmic expressions. In the next examples, we'll see that we sometimes need to use more than one property in the same problem. In this example, we'll first rewrite the cube root of y as y to the 1/3 power. Then we'll use the product rule to write it as the sum of logs. And then we can bring that 4 down in front using our power rule. And we bring the 1/3 down in front using the power rule. And that's the final answer. We'll begin example 4b by rewriting the square root of x as x to the 1/2. We then use the quotient rule and write the log of the top minus the log of the bottom. The argument of this log is a product, so we'll use our product rule and write that as the sum of the logs. Notice we're also rewriting 25 as 5 squared. The subtraction that was here required that we put parentheses around the sum. Next, we'll take the powers and slide them down in front of their logs. That's the power rule. We then distribute the negative through the parentheses. And the last simplification we can do, since the log base 5 of 5 is 1, we multiply the 1 by 2, and this is our final answer. Next, we're going to take our properties for expanding logarithms, and we're going to use them to condense logarithms. To do that, we could simply take the properties as written and just use them from right to left, but we often rewrite them in the following way. In example 5a, we'll use the product rule and write this as the log of 25 times 4, which is the log of 100. Since this is a common log, the base is 10, so we can simplify this because the exponent we have to raise 10 to get 100 is 2. In example B, we have a subtraction, so we'll use the quotient rule and write it as the log of 7x plus 6 all over x. To condense this log, we'll start by using the power rule and slide those coefficients up as exponents. We then use the product rule and write that as the log of a product. Since the 1/3 power is the same as the cubed root, we rewrite this as the natural log of x squared times the cube root of x plus 5. Now we'll look at the change of base property. It tells us that the log of m with base b is equal to the log of m with any new base divided by the log of b with that new base. Notice that b is the base that we do not want, and a is the new base that we want to change to. Note that we typically use the change of base property to change to base 10, common logs, or change to base e, natural logs. When using the change of base property to introduce common logs, we end up with the log of m over the log of b. Notice that b was the base originally, but now it's the argument of the log. And similarly with natural logarithms, we have the natural log of m over the natural log of b. In example 7a, we'll use common logs to evaluate this log. So we'll use our change of base formula to write this as the common log of 2506 over the common log of 7. We can use our calculator because we have a log button, and that comes out to approximately 4.02. In example 7b, we want to change the base to natural logarithms. So we write it as the natural log of 2506 over the natural log of 7. Our calculator has a natural log button, and when we use that to simplify, we get 4.02. So notice that when we used our change of base law, it didn't matter whether we used common logs or natural logs. In either case, we get the same answer. Finally, I want to emphasize that you should avoid the following common errors. None of the formulas shown on this page are correct, and you should not use them. It is a common error to think that the log of a sum equals the sum of the logs, or the log of a difference, product, or quotient equals the difference, product, or quotient of the logs. The quotient of the logs doesn't equal the difference of the logs. And our power rule only works if the exponent is on the entire argument of the log, not just part of the product of the log.